Hello, and welcome back to Our Living Climate, presented by the My Name is Climate Foundation. Last time, we discovered that based on simple physics, our planet should be frozen solid. Now, we solve the case of the missing warmth. We now begin Chapter 3, The Greenhouse Effect, Earth's Natural Blanket. Section 3.1, The Case of the Missing Warmth.
At the end of our last chapter, we were left with a profound mystery. Our calculations showed that based on the amount of sunlight it absorbs and radiates, Earth should be a frozen wasteland at a chilling minus 18 degrees Celsius, 0 degrees Fahrenheit. Yet here we are, on a vibrant planet with sprawling liquid oceans and an average temperature of a comfortable 15 degrees Celsius, 59 degrees Fahrenheit. There's a 33-degree discrepancy. The numbers don't add up. It's like auditing a company's finances and finding a massive, unexplained source of wealth that keeps the business thriving instead of bankrupt. For our planet, this wealth is warmth, and the source is not on the balance sheet we've seen so far. The missing piece of the puzzle isn't on the surface of the Earth, but floating just above it. It is our atmosphere. Specifically, it is a tiny fraction of the gases within our atmosphere that is responsible for this life-sustaining warmth. These gases create a phenomenon known as the greenhouse effect, and it is arguably the most important process in Earth's climate system. To understand it is to understand the very air we breathe.
Section 3.2, A Forgotten Discovery.
The story of how we discovered this effect doesn't begin with supercomputers or satellites, but with a simple experiment conducted in 1856 by an American scientist and women's rights activist named Eunice Newton Foote. Foote placed thermometers in two identical glass cylinders. She pumped the air out of one, creating a partial vacuum, and filled the other with normal air. She then placed them side by side in the sun. Unsurprisingly, the cylinder with air heated up more than the one without. But then she tried something remarkable. She filled a cylinder with carbon dioxide gas and placed it next to a cylinder of normal air. The result was clear. The cylinder containing carbon dioxide became significantly hotter and took much longer to cool down than the one with normal air. She concluded, with incredible foresight, that an atmosphere containing a higher concentration of this gas would give our Earth a higher temperature. She had, in essence, discovered the scientific basis for the greenhouse effect. Her work was presented at a major science conference, but because she was a woman, it was presented by a male colleague. For over a century, her contribution was largely forgotten. Today, we recognize her as a true pioneer of climate science.
Section 3.3, Molecular Gatekeepers.
So how does it work? Why do gases like carbon dioxide trap heat while others don't? The answer lies in the shape and structure of the molecules themselves. Our atmosphere is composed almost entirely of two gases: nitrogen, N2, about 78%, and oxygen, O2, about 21%. These molecules are very simple, made of just two identical atoms. Because of their simple, symmetric structure, they are mostly invisible to the long-wave, infrared heat radiating up from the Earth's surface. The heat passes right by them and escapes into space. But greenhouse gas molecules are different. Gases like water vapor, H2O, carbon dioxide, CO2, and methane, CH4, are made of three or more atoms. This more complex structure gives them the ability to vibrate and wiggle at just the right frequency to absorb the energy from the outgoing infrared radiation. Imagine throwing a baseball at a chain-link fence. The ball, A packet of heat energy would fly right through the large gaps. This is like heat passing through nitrogen and oxygen. Now imagine throwing that same ball into a net with a much finer mesh. The ball would be caught, and the net would shake and vibrate, holding on to the energy. This is what greenhouse gas molecules do. After absorbing this energy, the greenhouse gas molecule doesn't hold on to it for long. It re-radiates the heat. But, and this is the key, it radiates it in a random direction. Some of it goes up, continuing its journey toward space. But a significant portion is radiated back down toward the Earth's surface. This process, absorption and re-radiation of heat by these specific gases in the atmosphere, is the greenhouse effect. It acts as a delay, a temporary trap. It doesn't stop heat from escaping, but it dramatically slows down its exit, like a dam slows down the flow of a river.
Section 3.4, meet the key players.
Greenhouse gases make up less than 1% of our atmosphere, but they have an outsized impact on our climate. The main players in the natural greenhouse effect are water vapor, H2O. This is the most abundant greenhouse gas. It's a powerful heat trapper. You've experienced its effect on a humid, cloudy night, which feels much warmer than a clear, dry night because the water vapor in the clouds is trapping heat. Water vapor is unique because it mostly acts as a feedback, not a driver. A warmer atmosphere can hold more moisture, which creates more warming, a cycle we will explore later. Carbon dioxide, CO2. While less abundant than water vapor, CO2 is the primary control knob of Earth's climate. Unlike water vapor, which cycles in and out of the atmosphere in days, CO2 can stay in the atmosphere for hundreds or even thousands of years. It sets the baseline temperature, which then determines how much water vapor the atmosphere can hold. It is the thermostat for the planet. Methane, CH4. This gas is much less abundant than CO2, but on a molecule-for-molecule basis, it is much more powerful at trapping heat, over 25 times more potent, though it lasts for a shorter time in the atmosphere. It is produced naturally in wetlands and by termites.
Section 3.5, the blanket analogy.
The name greenhouse effect is actually a bit of a misnomer. A real greenhouse stays warm primarily by preventing the warm air inside from mixing with the cold air outside. A better analogy for what these gases do for the planet is a blanket. On a cold night, you pull a blanket over yourself. The blanket doesn't generate its own heat. You do. Without the blanket, your body heat would radiate away into the room, leaving you cold. The blanket works by trapping that heat and slowing down its escape, keeping the warmth close to your body. The atmosphere's greenhouse gases do the exact same thing for Earth. The planet is warmed by the sun, and it radiates its own heat. The greenhouse gas blanket doesn't produce new warmth, but it traps a portion of the Earth's outgoing heat, slowing its escape to space and keeping the surface much warmer and more comfortable than it would otherwise be.
Section 3.6, a life-sustaining balance.
It is impossible to overstate this. The natural greenhouse effect is a good thing. It is essential for life on Earth. Without this atmospheric blanket, our world would be a frozen, inhospitable rock. It is the delicate balance of these heat-trapping gases established over millions of years that has allowed complex life to evolve and thrive. For millennia, this system has been in a state of dynamic equilibrium. The amount of carbon dioxide released by volcanoes and decaying matter was balanced by the amount absorbed by oceans and plants. The Earth's blanket was just the right thickness. But what happens if that balance is disturbed? What happens if we start as Eunice Foote speculated over 150 years ago, to add more carbon dioxide to the atmosphere. What happens if you take a perfectly comfortable blanket and start adding more and more layers on top? You get warmer. And if you add too many, you begin to overheat. This is the critical turning point in our story. We've now seen how the sun provides the energy income and how the natural atmosphere manages that income to create a stable climate. Now we must turn our attention to the great regulators of this system, the oceans, the ice, and the clouds, to see how they influence this delicate balance and how they are beginning to respond to a blanket that is growing thicker every year.
End of Chapter 3. The Greenhouse Effect. That concludes Chapter 3. We've learned how the natural greenhouse effect acts as a life-sustaining blanket for our planet. Next, we dive into the first of the great physical regulators that helps manage this energy: the ocean. Join us for Chapter 4 by finding the playlist on our YouTube channel at My Name is Climate.